All right, welcome back, everybody. We're going to continue with some discussion from that 12.3, maybe go through a couple examples with that dot product work, okay? Also have a little brief notation and follow-up work from earlier vector introductions in 12.2, and then hopefully get a little bit of introduction to 12.4 as well, right? So kind of a lot to go through, but definitely all tied together with our discussion with vectors, okay? And so introduction to vectors and whatnot, coming back into it, right? And so again, for some notation and discussion here, which we've been practicing with this hopefully already, right? With our notation, we have our vector. We can call it, say, v with a little arrow above it. And we have our components of that vector, whether it be in two coordinates, two components, A and B, or X and Y. We start to give it that kind of organization in our coordinate system. The first coordinate, the X direction, the second coordinate, the second component, I should say, the Y direction, or likewise, if we have it in 3 space, just give it a new letter, W, that vector, right? A, B, C, or A sub 1, B sub 1, or right, A sub 2, A sub 3, some different notations here, or even that X, Y, and Z notation, okay? And so when we start to look at these vectors in our coordinate system, right, that vector can be anywhere in space, right? This can be that vector V, right, with those components A and B, okay? But we can shift that vector anywhere, being parallel, and it can be that same vector, A, B, or X, Y, when we started seeing this notation, right? If I plant that initial point, the tail of my vector where it's starting at the origin, then we can start to identify that these components, these pieces, right? There's our kind of A component, and there's our B component. That distance, if you will, getting back into our magnitude and whatnot discussions, those components for that vector, right? So that X and Y as well, A and B, these kind of parts building up that vector, okay? And then, though maybe a little bit more difficult to draw nicely for myself at least. There's my y-axis, x-axis coming out towards us, right? In 3 space, we can have that vector, okay, coming out here, that vector W, whether we call it A, B, C, or so on. But again, we can have that vector, whatever it might be doing, living here with initial point at the origin, identifying those components, the A, B, and C, the X direction, Y direction, Z direction. And so now we kind of get in this diagram a triangle component like so, right? Where now this is kind of your Z height. If we start to identify out here, right, there's our X component of it. How far out is our X? And then now how far in this direction? Again, I know it's a little bit jumbled here. There's your Y, but kind of having this triangle out in space, starting at the origin, measuring those components, okay? And so this would be that resultant vector of where X and Y would be, right? That'd be kind of like my vector V, if you will, before we start to give it height with that z component. All right, or we can start to label it as A, B, and C, or A sub 1, B, A sub 2, pardon me, A sub 3, a likewise method of describing. And maybe going back here, we start to see some other information, right? And so in this case, recall that our unit vectors with a little hat on them, right? These are vectors with magnitude, with length 1. And so in particular, we have the unit direction vectors that we can use. This I hat, right? This is the vector 1, 0 in 2 space, or 1, 0, 0 in 3 space. But this is kind of our unit x vector, right? The x direction vector giving us, okay, if I want to identify that I'm going in the x direction, I can use this vector I hat, just a unit in magnitude, either in 2 space 1, 0, or 3 space 1, 0, 0, right? That y and the z components are all 0, is purely going in the x direction, positive x direction, that is. Then we have our j, 0, 1 in the 2 space, or 0, 1, 0 in 3 space. There's my unit y vector, or my y direction vector. And then lastly, in 3 space only, right, we have our k hat, which is the unit vector in the z direction. That unit z vector. And so that's going to give us a way of rewriting our vectors, okay, in terms of kind of like these vector additions, if you will, building out these resultant vectors. So now we can rewrite vectors in terms of, or kind of using, those unit, sorry, writing too fast here, that unit direction vectors. Okay, that if we have that vector v in 2 space as a, b, right, or x and y, we can now rewrite it as how far we're going in the x direction, a times the unit I vector, right? Because that's just stretching that constant, that scalar a is just stretching that vector, that x component of it, plus b times that j vector, right? Or if we have a vector in 3 space, in R3, right, we have our I, j, and k components. So we're just taking those scalar multiples of those unit direction vectors, and we can start representing our vectors in this format. So we'll kind of bounce between these notations in representing those vectors, okay? And again, we start to do our calculations, whether it be a dot product, a cross product, which we'll talk about in section 12.4. We can use those formats to help us compute, okay? Right, so I think there was a question I had received from section 12.2 that asks to find like the angle between the vector, the resultant vector, and the x-axis, right? And so in this case, there's methods in 12.2 that can be used to find that angle, going back to trigonometry, but there's also work with our dot product from 12.3, that we can actually dot that resultant vector with, right, this unit vector, whether it be in 2 space or 3 space, right, to find that angle. And we can go through an example with that, okay, in just a moment. But here we are. So there's that work here. And so then getting into that discussion with 12.3 again, right, the dot product, and we'll continue that discussion in a moment. For the dot product, okay, or the inner product, another name for that, we had our 2 vectors, that a sub 1, a sub 2, a sub 3. This works, of course, with vectors in 2 space as well. But if we have our vectors, when I take that dot product, dotting these 2 vectors, we're just taking the product, right, the hence inner product, inside each of those components, A1 times B1, and then adding those similar products with our other components. And again, this could be reduced if we just have a vector with 2 components, or vectors, I should say plural, with 2 components, just working on those as a pair, okay? And the key statement here, notice our result, we have a scalar result. It's not a vector, it's just a numerical quantity. Any real number, positive, negative, zero is possible as well with that result, okay? And so then we have started to talk about then an application of that dot product, a use of that dot product, we're going to find the angle between 2 vectors. Okay, and we have this relationship that the cosine of that angle theta between those 2 vectors, and maybe we can draw it here, right? If we have vector A here, vector B, right? Since we can move it anywhere in that coordinate system, we'll have it so the tails coincide, and we want to find that angle between them. The cosine of that angle, so if we actually want to find the angle, we do our inverse cosine, but it's going to be the following. It's going to be the dot product between those 2 vectors divided by the product of their magnitudes, right? The length of those 2 vectors. And so this is going to give us some decimal answer. It should be some value between -1 and +1. Okay, if you're getting something bigger than 1 or -1, outside that range, something's going wrong, right? Because the cosine, as it is, only goes between -1 and +1, thing with a max and min. So that's going to make sure that as we're computing, we're on the right track. All right, and so then, and we'll go through an example of this in just a second, but now with that said, when we look for that process, okay, then in particular, 2 vectors are orthogonal, right? And that just means perpendicular to one another. If, and only if, when we take that dot product, we get exactly 0, the numerical value 0. And again, that just corresponds to, if that's our dot product, 0 over anything, over any real number constant, assuming these are non-zero vectors, right? The inverse cosine of 0, what angle has a cosine equal to 0? Pi over 2, or that 90 degrees. Okay? All right. So then we start to go through, right? That's a little bit of a recap, a little bit of a review. Let's borrow some of these problems here. And let's see here. Let's look at an example from our text. Let's look at problem number, let's say 18. This is on page 853 from section 12.3. Our directions: find the angle between the two vectors. And we can look on our calculator, get a degree approximation, right? And if possible, in terms of radians as well. But number 18, vector A, -1, 3, +4, and vector B, 5, 2, 1. So there's our two vectors. And we want to find that angle between these two vectors, right? So in order to find that angle between our vector, we know my general formula that's going to help us compute is that the cosine of that angle between them is going to be the dot product of the two vectors divided by the product of their magnitudes. So we have our two vectors. We'll do the dot product in just a moment. Before I get there, let's think about the magnitude. So the magnitude of vector A, the square root of the sums of the squares of its components. Squared, sorry. So we're going to take the square root, -1 squared plus 3 squared plus 4 squared, square root 1 plus 9 plus 16, 1 plus 9, 10 plus 16, 26, square root 26. I'm not going to be able to simplify that, unfortunately. Can't reduce that radical. The magnitude of vector B, and again, the sum of its components squared inside that square root. 5 squared plus 2 squared plus 1 squared. Square root of 25 plus 4 plus 1. 25 plus 4, 29 plus 1, 30. And again, I'm not able to simplify that radical. Next up, we need that dot product, right? So taking A, dotting it with B, that's going to be, go vector A was -1, 3, 4, dotting with vector B, 5, 2, 1. All right, so doing that work, multiplying. Again, I'm going to probably be a little bit tedious here, but I just want to reinforce this calculation. Multiplying component-wise, -1 times 5, plus now the middle component, the second component, 3 times 2, keeping track of those signs, the positive and negative. And lastly, 4 times 1. Computing there, -5 plus 6 plus 4. Okay. -5 plus 6 is 1, plus 4, +5 for that end result. So there's my dot product. All right, so putting this together then, so for my cosine of that angle between them, A dotted with B divided by the product of their magnitudes, dot product we did up here, +5. Magnitude of vector A, root 26. Magnitude of magnitude of vector B, root 30. That's a multiplication down here. And so 5 over, doing that multiplication we can do, but looking at this real quick, that's 2 times 13. This is 2 times 15. So we're going to end up with 2 root, whatever 15 times 13 is, real quick. Let me do that on my calculator. Again, we're going to do a lot of this work on our calculator anyways in a moment. But if I was to leave this in exact form, we're here. So doing that division, though, 5 divided by the square root of work. Just a second, sorry. All right, so doing that 2 root 195 in denominator, 5 divided by that, I'm getting this decimal. Okay. Make sure I haven't made any errors yet. All right. And though I hate to separate pages in that example, we'll do so right here. Okay. So if my cosine of the angle is that decimal, then my angle is going to be the inverse cosine of that decimal. And so in radian form, if my calculator is in radians, good. Inverse cosine, that last answer, I'm getting here in radians 1.390797,196. Okay, so approximately 1.39 radians. Okay. And that's just a little bit smaller than pi over 2. So let's see what that's going to be in terms of degrees. Okay, so if I change my calculator to degrees, and you can see I'm just doing this on a TI-84, changing my measurement to degrees. If I do the inverse cosine of 0.1790287185, hopefully I typed that in right. 0.1790287,185, right? So doing that recalculation there. My inverse cosine in terms of degrees, about 79.7 degrees. All right, so finding the angle between those two vectors. Okay. All right, so we can start to visualize if these are vectors for force or magnetic wave pulses, okay? What direction they're flowing out, those forces are, right? We can see how far apart, if you will, the angle between those would measure, okay? And so then, as a quick side example, that was that number 18, okay? Another example, I'm making this one up, but let's find the angle between the vector, let's say here, A being, I'm just going to make this up. Let's say this vector is at 3, 7, and that x-axis. Right, so there's a problem similar to one of those problems in the book. We can extend this even further into 3 dimensions if you wish. But let's just kind of get this visualization in. So one means of doing so, right, this vector A can be anywhere in space. But we're trying to figure out, okay, what is a vector, or what's the angle between this vector and the x-axis? So if I imagine planting the tail at the origin, having my vector A be here, okay, we're trying to find the angle between the x-axis and that vector. So as a right triangle, thinking about what we'll talk about later, these components, these portions of that vector. If this is my vector A, this side down here is going to be 3, this side 7, right? We're going 3 in the x direction, 7 in the y direction. So one means of finding that angle, okay, if we look at the relationship, the tangent of theta then opposite over adjacent, and we can do that inverse tangent. All right, so that'd be one method of finding that angle. Maybe in 3 space it might not be as clear to go through that route and think about which components we're using, okay? So that might be not as clear, depending, right? Well, then what we can do instead is that, well, if I want to find that angle between these vectors, well, the x-axis, I can use the unit I vector. That vector 1, 0, because that's the vector in the direction of the x-axis. Okay, so we can find the angle between those two vectors, or even do it with the y-axis, the j vector, right? So in that case, what we can do, we can take that cosine theta, a dotted with I, all over the magnitude of a times the magnitude of I, right? So up top here, 3, 7, dotted with 1, 0, over, I'm going to leave this in this notation, but the magnitude of I is just 1. So unit vectors by definition. So in the end, the real work is going through. 3 times 1 is 3, plus 7 times 0 is 0. The magnitude of A, the square root, 3 squared plus 7 squared, right? So we end up with 3 over 9 plus 49. Sounds like 58. Now we can go through the remainder of that problem. I know I'm going rather quickly, but we can stop and review this. Doing that 3 divided by the square root of 58, 0.3939192, so 9286. And in terms of degrees, doing our inverse cosine of that value, I'm getting about 66.8 degrees. Okay. All right. So there's hopefully a little bit of practice dealing with that dot product, usage, some of those calculations, some notation even as well. Okay. And so now, next up, going through there, let's do this example. Let's check out problem number 24, just the part A, I suppose. And we want to determine if the vectors are parallel, orthogonal, or neither, right? And so you might remember some of the work we've done back in algebra when we're looking at the slopes of lines and whatnot, asking are these lines parallel, perpendicular, or neither. So a similar kind of idea with these, right? Parallel, this means, right, the vectors kind of, I'll say, move in the same relative direction. Okay. And so our way of checking that, possibly, right, we can do the dot product and think about that angle. If they're going the same direction, right, our theta is going to be equal to 0 or pi 180. Okay. They're going to be either both going the same way or one's going to be backwards, right? 180 degrees, opposite direction, but same relative line. Okay. Or another way I kind of check for these parallel vectors, right? That the vectors are scalar multiples of each other. It's just the same vector with some constant stretching, compressing the other vector, right? So that vector A is just some constant times vector B. All right, orthogonal is when we check the dot product equals 0. Right? And lastly, neither. Right, of course, they're not parallel. They're not going to have constant multiples of each other. And they're not orthogonal. They're not perpendicular. Okay? All right. So with that said, let's check out these two vectors. So for part A in this problem, if vector u, -5, 4, -2, and vector v, 3, 4, -1. Right? And so checking these out, if these are going to be parallel, I would imagine that I would be able to take the same constant and multiply each of those components to obtain the second vector, right? So for instance, looking at my last components, the z components, if you will, if I want to get from -2 to -1, I would multiply by, right, 1/2 or divide by 2 basically. So I'd have to do that same action, divide by 2 to get the other two components as well. But that's definitely not the case, right? To get from 4 to 4, we multiply by 1. I can't multiply by 1 here to get 3, to get these to match. So in this case, since they're not these scalar multiples, I can't get that idea to work. These are not parallel. Okay. All right, let's check out the dot product. Let's see how this looks. -15 plus 16 plus 2. Right, multiplying, then adding. -15 plus 16 is 1. 1 plus 2, 3. That dot product isn't 0, not orthogonal. They're not perpendicular to each other, so they're not parallel, not orthogonal. U and V are neither, right, parallel nor orthogonal. Okay. So had we gotten one of those two statements to work, that they were scalar multiples, we're done, they're parallel. That dot product being 0 would have meant orthogonal. Done. But in this case, neither occurs, so those vectors are neither parallel nor orthogonal. All right. So with that said, let's check out one more application, that dot product. I know we've kind of laying it on here, right? But now let's start to look at these projections. Okay, so this is again an application of the dot product. So what we're going to start to see is that when we have these two vectors, let's say vector A and vector B, okay, we might be concerned with, right, and again, going back to like a physics example, if vector A, this is kind of, right, the path we're following. Vector B is this force that's being applied, right, like pulling a wagon, okay? As we're moving in that direction of vector A, only some of that force is actually being applied in the direction of A, right? Some of it is being lifted upwards, some of it is being lifted to the side to get that resultant total force. So we might be interested in, okay, how much of vector B is in that direction of vector A, right? How much of that force is going in this direction? This is being applied to that motion, right? So when it comes to work problems that we would calculate, the work being done to pull that wagon, to move that particle in this direction by a force moving this way, right? If we have these magnetic forces, electromagnetic forces flowing this direction, how much work is being done to move that particle through that force, right, in this direction? Okay. And so we can start to see like this is like how much they call it the shadow, how much of that vector B is down here. Okay. And so some statements here. We have our scalar projection. Okay. Or of B onto A. Let's get that language in there. Right. So we're projecting, we're pushing, or identifying how much of B is going in that direction of A. That's going to be this component, comp, with a subscript A of that B, right? So again, I kind of imagine I'm pushing B onto A. So A is my subscript. That's the direction we're looking towards, A. And this is how much of this vector is in that direction of A. And we can compute that by taking that dot product, A dotted with B. And again, it's commutative, so if you want to put B dot A, that's fine. And we're dividing it by the magnitude of that vector A, right? How much is going to be in this direction. And it's a scalar projection. Dot product is a scalar divided by a scalar. We're going to get a numerical value. So this is, right, a numerical, right, scalar result, kind of identifying, I say kind of how much of vector B is in the direction of A. Okay, move that up a little bit. So again, thinking about those forces, how much of that force B is moving in that A direction. Okay, and then next up, we have our vector projection of B onto A. This is labeled the projection of B onto A. So the subscript is A. And now we're actually going to give it a vector component. Okay, give it a vector result. So in this case, start off with our scalar projection, that component, how much of B is in the direction of A, but then we're going to multiply it by, right, a unit vector in the direction of A, or simplifying this down, this is A dotted with B over the magnitude of A squared multiplying vector A. So now this is going to be a vector result and now this produces, right, an actual vector with the magnitude and direction of the portion of vector B along that vector A. Slide that up to read. Right, and so again, I understand this and kind of put this together mentally for myself, is we take these forces and we start to separate into these components. So how much of that force of pulling that wagon, moving that particle, is going in a particular direction of vector A. Okay, so the component, the scalar projection, is kind of giving us that magnitude, how much, what part of B is going in A's direction. And the vector projection part is now, okay, if I wanted to start to break that down and use that as a vector to do calculations, like so. So basically just kind of stretching a unit vector in the direction of A, multiplying it by that component of B in the A's direction. Again, I'll let that kind of settle in. It does take some time and thought, but relying on that physics work predominantly to do that process, okay? All right, so let's take a second here. So now with that said, all right, we can do some examples. I'll give you some time to practice. I've put a list of problems from the sections to practice on the Canvas site. Let me introduce, though, this next calculation just to get us started with that work, right? And so now we're looking at the cross product, another operation with vectors. Okay, so notation-wise, we have vector A, A1, A2, A3, vector B, B1, B2, and B3. When we take this cross product now, okay, take a second to write this all out. When we do this calculation, pardon me, we're going to use the determinant of a 3x3 matrix. Across the top row, we have our unit vectors I, J, and K. Then we start to fill in, right, kind of keeping track of that order. A vectors first, so A1, A2, A3. So we're kind of labeling those different components, the directions, and those components associated from the first vector, the bottom row, those components from my second vector. And now we're going to compute that 3x3 determinant, right? So if I expand across my top row, it's going to be here, right? Crossing out that row, that column. We have this smaller 2x2 matrix, right? So doing so, A sub 2, B sub 2, A sub 3, B sub 3 times our first row component. Then it's always going to be a subtraction. Now crossing out that row, that column. Now that minor, right, that smaller 2x2 matrix left over, A1, B1, A3, B3 times our J component. And lastly, with an addition, top row goes away, Last column goes away, that smaller matrix. A sub 1, B sub 1, A sub 2, B sub 2 times K, right? And doing those 2 by 2 matrices, determinants, that cross product, that multiplication, subtraction, right? Watching our signs here. And again, I don't imagine memorizing really bit by bit this formula necessarily, like all these terms. More or less this process is what I go through each and every time, being careful about those signs. But notice what happens. We're left with those I, J, K direction components. So what we find is we get a vector result from the cross product. Okay. And what we find is that when we do a cross product between 2 vectors and we get a vector result, and we call it C, the key property here is that vector C is orthogonal. It's perpendicular to both vector A and vector B. So this is producing a new vector that's going to be perpendicular to the original 2. And we start to define these surfaces and going through work practices with vectors and 3 dimensions, having a vector that's going to be orthogonal perpendicular to 2 vectors is going to be an important aspect, right? But again, I just wanted to introduce that action, and we'll get through the properties and practice some calculations with this as we go forward, okay? All right, so a lot to digest in that lecture, I know. Some of those applications, those uses of the dot product, and now this introduction to the cross product, but hopefully gives us enough to get going with that 12.3 work, and it's starting into 12.4, okay? All right, if you have any questions, please let me know. I did post those practice review problems, right? Not necessarily homework, because I'm not collecting it, but stuff to kind of get practice working on with this chapter 12 information of vectors, okay? All right, I'm gonna stop sharing, stop recording, but if you have any questions, concerns, please email me, contact me to let me know. All right, take care.